So thank you very much. Very honoured to be presenting here. I was trying to remember the last time I was here. It's for a nice semantics conference, maybe 10 years ago. So it's very lovely to come back to Leipzig and to present on my current work. I'm going to talk about how we're using FAIR data inside AstraZeneca. And what I'm trying to bring home is how we have to approach it from an enterprise perspective, which is different to the way that we approach it on the web. But we take inspiration from the web, and we're obviously guided by those 10 principles and 13 sub-principles that exist around FAIR data. I'm going to talk about it in 3 sections. I'm going to first talk about the new science that we're enabling and how we're trying to move people away from doing search to doing information discovery. Then I'll talk about standardization as the only way to scale. And this isn't just about the data, this is also about the infrastructure that we use. And finally, I'm going to talk about our approach to FAIR data-centric information architecture and how we're hiding the semantics from the rest of the business to aid the adoption. So why are we doing this? We're doing this because the science is evolving and we're asking more and more granular questions of the populations of patients and looking at diseases in much more granular form. So we can take the example of cancer. Many years ago, we just talked about people having cancer. Now we talk about people having cancer of an organ. And then we started to talk about cancer of cell types and non-small cell lung cancer. And now we talk about the mutational profile of the cancer. And as we drive deeper and deeper into the understanding of the disease, the need to have subjects, patients that match that profile to be able to do data science on and to gain new insights requires us to combine data from across broader and broader pools of different data sets from different groups within the company, from different clinical studies that have been run within the company, and different functional groups, and with CROs and academic collaborators. And all of this means that we have to move from talking about the clinical study to talking about the subject to talking about a subpopulation and the samples within that population. So we're moving our science from what was a very fragmented state to an integrated state where we can talk about it and explore it in this fashion. So the tool that we've built has a front end which we refer to as scientific intelligence, and this is where the scientists are able to start to explore the information space. And we started by gathering use cases, so we've always been very pragmatic and very use case driven. I'm not going to read through these examples, so I'm sure you can follow up afterwards and look at them. But essentially what we went through all of these, as all of you will do with your use cases, is to look for the entities that exist within the questions and then identify where that data can come from and then how do we pull that together. And so we have our use cases, we identify our sources, and I'll come back to this idea of platforms and the data mesh architecture that's associated with that. And then we bring it together through a knowledge graph. We refer to this as a knowledge map, and I actually introduced this when I first joined AstraZeneca. There was a lot of conversation of we need a knowledge graph, right? And is it a label property graph or is it a RDF graph? And there was a religious war going on, as I'm sure you've all experienced in this conversation. And so what I pointed out was, well, there isn't going to be one graph, there's going to be lots of graphs. And we're going to use different graphs for doing different things and different technologies for doing different things. And I said, there is this idea of a knowledge map, which is really about integration. It's about helping people navigate and explore information space. And that's what we're building with an RDF graph. And then there are analytical knowledge graphs, which are really like applications. And maybe they're the right tool to be using as a label property graph. And just introducing that as a conversation created enough headspace to allow people to actually work and to move away from the religious war and for us to progress that conversation. Now we need to, we all know that building a knowledge graph and our graphs are super cool and we're really excited by them. But my end users care about an interface. They don't care really about how the data was put together or anything of the hard work. They want a nice interface that they can use. So we use a tool from a company called OntoForce. Keep mixing those up, and apologies to my colleagues here on that. And that's our scientific intelligence, so that's our front end. So people can search that and then they can submit a request. And in our case, because we're dealing with clinical data, we're dealing with subjects who have participated, they need to go through a consent and compliance process. So we then have this process called an IDAP request to request access to those individual patients. We have in here essentially, and apologies, I can't really show you the data. I hope you can appreciate this is clinical data of individuals and we have to respect their privacy. So I can kind of show you the general structure. So we aggregate information around studies, the subjects that participated in those studies, the samples that have been taken from those subjects, and then the data that has been generated on those samples. So this could be digital pathology, so immunohistochemistry, staining from images, or it could be gene sequencing, proteomics, metagenomics, etc., etc. But essentially, we take all of those observations around that and bring them together. And you can see the graph here, and at the study level, we have information about basically summary information about the study and information specific about the study. So the number of studies by indication or by drug, but also at the individual study level, the title, the status of that study, the phase that it went through, the number of patients, etc., etc. And then as we move down into the subject, we now have summary information about how many adverse events of a particular type were observed at a summary level, whereas at the individual level we can go down and actually look at their demographic information, the adverse events, the lab tests that were performed, their vital signs, those sorts of things. We don't have all of the clinical data that's generated around the study. This is about the data that helps the scientists find the right subset of patients that they're interested in, and then they request that and they get access to the full data set. So we have this sort of degree of separation that occurs. Get down to the specimen level, so these are the blood samples or the biopsies that were taken. And again, here we can say the number of samples that were taken, the sorts of tissue that was extracted, the preservation method, the availability. Is it still available as in inventory? And people can now ask for if there is wet samples in our freezers that they can request as a result of doing data science, so that they can then test their hypothesis by repeating new science against it. And finally, we get down to the observations, and so these we can start to look at things like the number of images that were captured, and we record both the medical images, so X-rays, MRIs, etc., as well as things like the digital pathology staining of slides and so forth. And we can go down and tell you about the variants that were observed, so the tumour profile of a patient and those sorts of things. So we get down to quite granular information, and all of this is about driving people to be able to find data. Now, the use cases that we then see people using this for are doing a number of different things, and these tend to be difficult queries that they weren't able to do previously, or if they did them, it took them a very long time to do it. So there are three examples here. One's a landscape review. So we're often trying to understand, how much data do we have across this profile? So it might be the different stages of a cancer and the different types of populations that they generally see, and they want to know, how much data do they have that has a proteomics measurement and has a particular staining type analysis that's been done on it. And the questions they're asking strategic is, should they be investing in purchasing more data of this type to help fill out that the holes in that matrix. These things typically take up to 6 months to pull together, because it requires the person pulling the information together to go around the various different labs and talk to the various different experimenters to gather that information together. We can now do this in minutes. It's just a query, right? So whereas it was only done where it was really needed, now you can just generate these views whenever you want. Study design optimization is another use. You're trying to learn from the past as to maybe how many subjects you need to achieve statistical significance in the study, so that it's powered correctly, as they refer to it. And so you want to look at legacy patients with a similar profile to the one that you're going to include in your future study, and see the variability of the data for the particular lab tests that you might use, and that will help you select the different lab tests that's there. Again, this can take weeks, to request someone to find the studies that might be relevant to you, to get the data back, and then you've got to align all the data, and then you can do your analysis. We can now enable our study designers to do this on the fly using data directly within this tool. They don't even have to submit a request for the subject, the data in many cases. And finally, that cohort selection, that one that I started with, I have a indication, so non-small cell lung cancer, I want to treat it with this drug, and I want to know what this particular adverse event, and does it have this sort of imaging around it. That was weeks again, and now it's down to minutes. And these are really enabling the scientists to do it. We recently had a case where one of our data scientists wanted to produce a model for neutropenia. So neutropenia is an adverse event during chemotherapy, which results in your blood immune system basically being suppressed. You can put people on recovery treatments if you can spot it happening, and that allows them to maintain additional rounds of chemotherapy. So it's really important. It can have significant impact on patients. The team he was working with only knew of 2 or 3 studies that would have the relevant data that they needed. He was asked to have a look in scientific intelligence. He managed to over double his subject, his sample size, and also had confidence that asking for those samples, that data sets to be processed would result in data. This is exactly why we built it. We're enabling that new science by helping people to uncover our unknown knowns. Now, the really big challenge with those questions is getting people to understand what is now possible. And the other issue is that scientists only ask these big, complex questions maybe once every 6 months. Because once they've got their data set, they go off and they go and do their work for the next 6 months, and then they come back and do it. They don't build familiarity with the knowledge graph and the underlying structure, and therefore it can be quite intimidating for them to know exactly what's the best strategy for them navigating it. So we're building these hugely powerful tools, and as we bring all this data together, we're building something really quite complicated for people who aren't in there every day. And it's very difficult to build a UI that is really that simple. Now, maybe we can come on to LLMs helping us in this space. But what I equate it to is, back when I did my PhD, I went to this really big building that was full of books, all this aggregated knowledge, and there were these librarians that could help me navigate this space. I do wonder if we need to bring the librarians back, and this is what we're exploring in our team now, is to try and bring information practitioners back into the fold and to help them use this so that they can help people to navigate this information space. So I'm now going to talk about standardization, and it's the data that's important. Let's not get hung up on the tooling that sits underneath it, or let me put it another way. If you have to do it all yourself, you'll kill yourself. And that's what we found. So this is just to give you a picture of what we're dealing with. We're dealing with data coming from about 13 different systems, which we now have platforms that aggregate the information across those systems and try to provide us a data product that we can consume from each of those platforms. And I'll come back onto this, but it's the study, the subject, the imaging, the omics, and the sample. Plus, we're now looking at real-world evidence, so health payer and hospital data, and we're starting to look back into the preclinical space, into the safety data as well, so we can do translational medicine across this. Scale, and as you broaden it, brings a headache. And we tried to do all of this ourselves. And when we started, we were having to help capture the information, help curate the information, help verify the information, and then we could use it. I have a team of 6, right? This was killing us, right? There was no way we could do all of this. So the questions we had were, how do we simplify the way we do our verification? Could things like the data mesh and data products help? How do we standardize that? How do we enable other people to do it and to allow us to maximize our data engineering skills without having to do everyone else's work? So how do we better manage that graph ecosystem? You know, we spent too much time just managing infrastructure because we had the smorgasbord of open source tools here and some proprietary tools, and we were perpetually spending my rare and very valuable scientific semantic engineers who spent their time managing the infrastructure and getting it all to work. How do we evolve from virtualization? So we were using a virtualization solution. What we realized is that in our case, scientific data is pretty much static. Once you've done the experiment, you really doesn't change. So there's no value in virtualization. You can process it once, just make the most of it. And then also, how do we orchestrate all of these things? Because it was, to be honest, it was a mess, as you might imagine, with all of these independent pieces. And then the other question we had is, how do we democratize the graph? How do we make it easier for people to take advantage of what we've put together? How do we make it play nicely with the rest of AstraZeneca? Because, you know, the rest of the world that we live in is a relational world, and they have a whole set of relational tools. So how do we play nicely with it? We can't expect them to write Sparkle. So how do we complete that journey? And can we extract more value? So the answer here is just standardize, standardize, standardize. You know, don't be precious about your cleverness at being able to build and combine the best in breed of open source tools. Look to see how you can do it. So from the FAIRification perspective, we had the data mesh movement going on within AstraZeneca and the idea of data product. So the idea there is that a domain produces a data product which is designed for reuse. And so we now encourage our domains that were formed to produce an aggregation across all the subsystems that they have within their domain to present out and to share with the rest of AstraZeneca. So now I'm no longer going to source systems, I'm going to a platforms product, and they're responsible for the cleaning up and the FAIRification of the data. And we'll talk again about how we're driving better interoperability into their data. We moved to using a combination of what turned out to then be default infrastructure, and basically we use Snowflake now for our storage and DBT to do a lot of our cleanup. Now we do a lot of work, and this was a really important piece. We chose to do an awful lot of data cleanup and data wrangling in SQL because we can get an awful lot of SQL engineers, and I much prefer to use my semantic engineers to do semantic things rather than just doing data wrangling and cleanup, right? It's not to say one is more important than the other, it's just that I can get an awful lot of engineers with SQL skills. So we've focused on doing as much cleanup as possible in the SQL space. And so we've standardized our tooling there, and we use Airflow as our orchestration in that space. And then we also do quantification of FAIR. So we've introduced Python libraries, mainly based around the Great Expectations library, to start to quantify every step of our profile. So we check the data on entry, we check it all the way through, and we check it on export. And the really other nice thing about DBT is we get auto-cataloging, or auto documentation of all the transforms that we've done during the process. So we can really produce, if we share that data, we can produce it with a full lineage background around that. And even better, we can get other people to use this because it's all part of the standard stack that's now being adopted by AstraZeneca. So the patterns that we've identified, we can share as learnings to get those platforms to help clean up their data. We can take the SQL that we've generated to do the data cleanup, and we can just pass it to them and say, well, this is what you need to do, and then they can go and implement it. We chose to go with corporate memory now at our graph level to manage that ecosystem. And we went there because it's a solid bit of German engineering, to be brutally honest with you. It is well thought through. It eliminated the smorgasbord of things that we were maintaining. We could go to eccenca and get them to, well, they took ownership of packaging it up, managing the security updates, managing the patches, evolving that ecosystem, introducing new capabilities. My engineers can now look at working on the data rather than the infrastructure, and that's what we want to do, it's the data. And finally, the other piece that comes with this is both some really nice import data pipelining capabilities that allow us to now have engineers who came from the SQL world to work with semantic mappings. My BA, okay, my BA Nicola is not a normal BA, I will accept this. but now she actually does an awful lot of the mappings herself. So the proof is in the pudding of what the corporate memory promised was that they would lower the entry level to be able to work with semantic tools, and that's exactly what they did. And at the other end, it's really smart that the same pipelines that you effectively use to import your data into the graph, you can use to, or the same tool set you can use to export the data back out into the various formats that want to consume. So we're getting it back into the tooling space that the rest of AstraZeneca works with. Now, all of this is underlined by us producing controlled vocabularies, so sets of terms that are defined against a class and contain the URIs, or as we refer to them as PIDs, so persistent IDs. We've invested and continue to invest in our URI patterns. I don't think I realised until we started to do this just how much concrete I was pouring when we set our URIs, and getting those right and getting those consistent is absolutely at the heart of everything. And I still have sleepless nights over our conversations around URI patterns because chipping out concrete is very hard. And we have a reference model that we construct in OWL, and we build this outside of corporate memory, and then we import it. And our reference model is at the heart of everything that we do, and that's what we're going to talk about next. We're going to talk about this information architecture and how we bring it together, and how we're driving FAIR into our organisation. So I'm sure you're all familiar with the idea, or hopefully you're familiar with the idea of data centricity, the idea that the observation that our data outlives all of our applications. So why allow our applications to shape our data? We should invest in the data and then have our applications visit the data. For us, I'm going to slightly bastardise that term, and whilst I say we're doing data centricity, I think the likes of Dave McCoon from Semantic Arts would say that I'm really building a domain model and I'm driving it around that. And yes, I am. I'm driving it around the science that we do in R&D. And what we're doing is we're transforming the language in many respects from the underlying systems that capture the data and pivoting it into the language and the concepts that the scientists are using so that they can start to query it in terms of the things they're interested in rather than the systems in which it was captured. This slide, I'm not going to read through any of the text on it. I'm sure they'll be shared afterwards and you can look at it. Really all I'm saying is that the blue ones are system-centric FAIR. And the idea here was to start to introduce the idea that there could be different degrees of fairness. Now, we all know that FAIR is contextual, but this was at least a way of starting to get the organisation to think about quantifying FAIR. And we developed this with the information architecture community. And we said levels 1 to 3 really represent system-centric, and then levels 4, 5, and 6 represent knowledge-centric. Now, I'm not going to talk through this slide. What I'm going to do is talk about this degrees of fairness in terms of a shopping experience. So, the lowest level of FAIR, I am going shopping, and I go to a junk shop and I'm looking for shoes, footwear. And everything's random, there's no organisation whatsoever, there's no sense of providence. I might find a flip-flop and a diving boot. Yes, they're both in the class of shoe. I would be very interested in the social situation which will require me to use a flip-flop and a diving boot. If people have suggestions of a fancy dress party that I could attend, I'd be interested to know. But the point is, it's random. You don't know anything about what you find. Good luck. And then we can start to think more and more organisation. So the first step up from this might be a car boot sale. Every stall at the back of a car has what that person is selling. They've probably organised it to an extent that the DVDs are here and the books are here and the children's toys are here. But the organisation is bespoke to them. You don't know what's going to be on their stall versus the stall next to them. If you want to find a thing, you're just going to have to search through the entire market to try and find it. Good luck. And then we can start to see more organisations. So we can think of something like a street market, maybe a Moroccan street market. And here, you start to see aggregation of stalls of a type together. So you might get all of the spices in one area, you might get the vegetables and the fresh meats in the other, and so on and so forth. And you can go to, say, your spice stall, and you can see that the different spices are well labelled. You can talk to the proprietor about what each spice is, and they can maybe tell you, oh, well, this one comes from that farm, or this one comes from this place. But the layout of the stall is going to be bespoke to them. It's going to be different to the one next to it. You've got no sense of quality, maybe, or authenticity, not authenticity, but, provenance is really quite limited, and so on and so forth. So again, it's more organised, but it's not really there. And we would equate these three levels that I've just talked through as being system-centric behaviours. If we think of shopping we go to our local 7-Eleven, sorry, I don't know what the German equivalent of this is, your local corner small market. And when we go in here, we see that next level of organisation. So the goods are organised into aisles. The aisles have labelling above them. The categories within them, so you might see baking goods, vegetables, you might see cleaning products, right? They're all gathered together. And you can go there and you can pick up a product and it says provenance, where it was made, it will tell you about the ingredients and so on and so forth. So you're now starting to deal with much more organised data. And the other thing that comes with this, if you go into a 7-Eleven almost anywhere in the world, that same navigational structure is existent in all of them. So you can quite easily navigate from one to one. So you're seeing at least scaling across instances of this experience. The obvious next step up is something like a supermarket or a hypermarket, where just the scale of products now are so much greater. But the other thing that we see when we move there is, again, all of that structure that we saw at the small scale in the local mart, but now we're starting to see displays of things that are around events and often seasonal. So we've just come out of Easter. So in the UK, we will see all sorts of things gathered together in a single display, not just the chocolate eggs, but maybe the lamb. We like to have lamb at Easter. There might be some wine, there might be some gift cards, those sorts of things. So it's starting to present the data in terms of the experience that people are interested in, rather than just the organisational layout on the standard form. When we finally get to what we would refer to as our level 6, we are really moving away from the physical limitations of the products being displayed. So you can go to Amazon and you can see almost anything there. Yeah? You can explore in any direction. You've got recommendation engines suggesting things. So they're almost creating those experience displays on the fly for you. And we're also seeing services being built off the back of this. And the example I was quite struck by when I started doing this was I was looking to cook some slow-cooked pork, and I just Googled recipes, and I found one I liked, and I was reading through it, and there was a button that said, add the ingredients to your loyalty card. So I was on a recipe website, click the button, and it would have assigned all of the things I needed to do that to my Tesco's loyalty card, so that was then added to my next order as a thing. So my experience has been completely transformed from having to go and find the recipe and find the components to, oh, I'll just have that because that's what I want to cook, right? And it's this transformation from the individual things to the experience that is the really important piece here, and that's what we're trying to deliver. So how are we doing this? Well, I'm going to use this this framework, this device here, to talk about our approach. What we do is we've recognised that to get fair data, we need to combine the reference model, the control vocabulary. So the reference model describes the things that we have. The control vocabularies categorise and describe those things that we've identified, and then we put the URIs back into the data, and if we do that, we can then build our knowledge graph. And I'm going to talk about these in this, each of these legs of this as my colleague Derek referred to as a three-legged stool. He was so impressed that he actually went away and made a stool. So sometimes your conceptual models do get turned into physical models. And I'm going to talk about it with meaning. And I'm going to start there. And in the words of Dave McCoon from Semantic Arts, start with meaning. So we're going to talk about the model leg. Here, in most companies, and most projects I imagine as well, will have conceptual models that you will have put together. In large enterprises, they're probably a diagram that sits in IDERA that gets updated once every 3 years. It contains a rich set of information, but it's a conceptual model. The information architects look at it and they think this is really nice, but nobody else cares about it, and it gets lost in translation all the way through to the physical model. We really like it. We really like the effort that the information architects put into disambiguate and identify the entities in there. And so we take the conceptual models and use them as inspiration. And within these models, you have the blue folder or boxes in there are the classes, essentially. And what we decided to do was to build small models that we refer to as our entity ontologies that correspond to the classes in there. And we did this so that we could have modularity and that we could evolve them and version them independent of each other so that we had great flexibility in going forward. We assumed at the start that we would get it wrong and we would have to evolve these things as we discovered the data that would allow us to expand the use cases that we had. So we build our ontologies, and in these, the orange post-it notes, which you can vaguely see, represent the classes, and the green represent the attributes in there. And you can see that within an entity ontology, there is a top-level class, and then there are a series of subclasses as well within it, because they model things like a clinical study, well, a fragment of a clinical study, or a biosample, or a drug, and they are significant models unto themselves, but we built them as components. And then what we do is we import them into our application ontologies that we create. So we pull those forward and we put them together as Lego blocks to build these application ontologies. And then the FAIR diagram on the far right, the honeycomb thing. This is a motif that I picked up from a guy, Dan Gershwind at Amgen, and it's a really powerful device for talking to leadership and abstracting them away from trying to present you that Miro board diagram of an application ontology. If you can present it as this honeycomb where the filled in hexagons represents concepts and the links between them represent the major links in there. I can talk about it in terms of here in the center, you've got clinical study, and then the blue one to the left is drug, and then the one above it is indication. So you can say, okay, I'm interested in clinical studies where drug X and indication Y were run, and you can start to talk through the hexagons, and it becomes really easy for them to understand or conceptually understand what you're talking about, rather than trying to walk them through a model like the application ontology that we've got there, or even trying to show them a turtle file if you're being particularly mean and vicious. The whole point of this was to really go for an acceptance that this was going to be organic and that we were going to evolve the reference model over time. We started with 3 different groups who were all working around similar sorts of space, and unsurprisingly, you see a common motif of basically clinical study drug indication falling out, as you can kind of see in the top model. And then we saw that in the model we were doing with precision medicine colleagues, and then there was another model going on, the Thrive one in oncology. And we said, okay, can we bring these together? This was the proof of the pudding of taking our entity ontology approach. The answer was yes, and then we've been able to continuously evolve it based on the emerging scientific use cases that come forward. So we add complexity in rather than try and design everything up front. We take an agile approach to this. The next leg is the control vocabulary. So we've identified in the model the things. We want to be able to describe and to decorate the things with the categories that they apply to. When we first started our first go at this, we were all working as independent groups, and the team that were the reference data management team who were doing this did their best. And this isn't a criticism, it was a learning. What they ended up with was essentially lots of vocabularies being supplied from various applications that they were overlapping, so the same concepts would appear in them. So what we effectively had was just a pile of Lego bricks on the floor with no ability to really have any control. So we introduced the idea of a data office, and the data office is it's like an editor. It's trying to drive consistency of house style across our vocabularies that we build, and to build them in a coordinated fashion, and to build them as atomically as possible. So we might see in the data blood EDTA. So this is a column that's showing the biofluid that was taken as a sample and the preservation method. So blood is the fluid and EDTA is the preservation method. We wanted to not build these concatenated vocabularies. We wanted to build a CV for blood, or CV for biofluid, and a CV for preservation method, and then allow people to bring them back together. And this is like a faceted CV within SCOS. And by doing that, we had absolute atomicity in our build of CVs. And the first level of that is what we refer to as local. There has been semantic drift around these terms since I produced this slide internally, but essentially a local CV was a CV that is atomic, designed against our framework, but is for a very narrow use case. So it might be for just a group that wanted 2 or 3 terms in there. And then we see foundational CVs really being that CV as it starts to mature, and we add new terms into it, and we extend it, and it now is being used by multiple groups, and so on and so forth. And then we allow collections and faceted CVs, these ideas within SCOS that allow us to create slices through one or more control vocabularies that people can then utilise to actually include the values in their data. And we use SCOS Excel, and we've extended it slightly. Here we see a CV for a concept scheme for country, and here we see the example of Switzerland. And on the right-hand side, we can see the different preferred labels for the countries and in different languages. So we're providing language tags in there as well. We include the alt labels. We include hidden labels for spellings and things like that. Terms that we want to keep a record of, but we don't want proliferated. And then we also include, for all of the labels where it's appropriate, the schema that it came from. And this is really important for us to actually turn our control vocabularies beyond simple lookup lists to actually being a Rosetta Stone that allows us to translate between schemas. So I can say, oh, I want the English country names. Or I could say, I have the ISO 316 two-letter code CH. Translate me that to our pref label. But equally, I can say, oh, I need to translate the ISO 316 three-letter code to the two-letter code, and I can use the CV to do that and that translation as well. Most people don't care about doing that, right? Those of us in the semantic space really do care about being able to do these really cool and useful things. Most people just say, actually, I've got this term. Can you give me the URI that I need to include in it? So we try and hide the semantics and allow people to just deal with the thing that 80% of the world wants to do. And that's really where we now start to talk about the data. So that level 4 data, that first local store, that local mart, for us, level 4 data, or for me, level 4 data means that you have catalogued your data. So you have recorded the data set, the data system, the data product in the catalogue. So people could search for it and find it, and you probably provide some minimum metadata around that. Once they've found it, there is a mechanism for them to request access to it, and there is some documentation about the reuse, so licensing or constraints that exist around it. But this hasn't done anything for the interoperability. If I want to combine those data sets, I've still got a lot of work to do. So I couldn't resist this to say that we were far from FAIR, and we had to go further. And so if we want to go further, we've got to tackle that hard problem of how do we make the data interoperable. And that really means using those controlled vocabularies that we're constructing and taking the data and putting the PIDs into the data. And that will deliver us a level 5 product. So now we're talking about how the controlled vocabularies and the data come together to achieve that. What does it really mean? You know, I've got dirty data on the left-hand side of this slide. And in the first column, there's a series of clinical study identifiers. One is a study code, one is an acronym that people use to describe the study because nobody remembers the D codes, and then there is a legacy code. What we want from a data perspective, we just want these standardized. So what we need to do is provide a service that allows people to submit those terms and just get back the pref label and the PID for those terms. And that's what we're asking them to do, is to just curate their data by looking up against the controlled vocabularies where they're present. And if they do that, they're going to create interoperability. And they will create interoperability irrespective of the technology that you then want to use that data in. So if we have PIDs, URIs in our data, we have fully disambiguated the meaning of that value. And I have absolute confidence that if I see the same PID in another data set, I can join those two things together. And that has huge benefits, whether I'm building a relational database, whether I'm putting the data into a labeled property graph, or whether I'm building an RDF graph, or whatever other esoteric use of the data you want to do. We are eliminating the biggest hurdle to the reuse and the recombination of that data. And you know, you can say 80% of data science is spent wrangling data. If we can reduce that by 40% by doing this, you know, that is a huge saving to our scientists. They can get on and do their experiments rather than just try to fix their data. So the control vocabularies and the model. We took a really early decision to create a separation between the two. Now, you'll see many ontologies in the life sciences area which are a combination of the vocabularies that describe an object and the model that relationships between the class and the classes and the relationships between them. I think the top quadrant referred to this as classonomies, and we decided that we wanted to create a separation between them. So we create our reference model, which consists of is built in OWL, and it consists of the classes and relationships between them and the attributes, data properties that are associated with it. And so on the right-hand side, you see by a specimen, and you see it represented by a single orange post-it note. And then on the left-hand side, you see that expanded into the full entity ontology, and you can see that there is a class, subclasses, there are a large number of green data attributes. Just so you know, we support the string version as well as the class version of everything, so that if there isn't a vocabulary present, we can still deal with the data. But you will see that on the right-hand side of that post-it, that box, there's a whole load of blue things. Each one of those corresponds to a controlled vocabulary that we've created to describe this class. So we build all of those controlled vocabularies using SCOS XL, as I described, and we define the relationship within the SCOS metadata, saying this refers to this class, and in the class in the OWL, it says the reverse, so that we can then plug these things back together. But we create this separation because it allows us to create services that are really just focused on that use case that people wanted, which was to do this. They don't need to know anything about the semantics to be able to do this. And if I want the rest of the engineering teams to do this, I want to make it as easy for them as possible. We've gone further, and this week my team have now created a very big wide table of all of the control vocabularies that we've produced in Snowflake as just the pref label, the PID, the pref label, and all the synonyms. So SQL engineers can just use this common table to just do a lookup and SQL query it and get their data back. It's about making it as easy as possible to consume this. so that they will put all of these PIDs into their data. Because we all know that if we can get the PIDs into the data, it's going to solve this problem. If I don't have disambiguated data, when I map my data into the graph or into the relational database or whatever, I need to have some sort of mapping table, a set of instructions to tell my engineering team that this, it goes there and is equivalent to this, and that's how they join together. We want to get away from that. And so what we've done is we started with our reference model. We identified the thing. We worked out how we were going to describe it with control vocabularies and put it back in, and then use those control vocabularies to update the data. But what you've, of course, done is effectively bake your reference model back into the data without anyone having to know about the reference model. And now, things just snap together because they all have PIDs and they all align and they're all consistent. All the namespaces map and we can join them together. So it's just like snapping Lego blocks together in the instruction set, and it's already built into the data. So what have we actually achieved by doing this? Well, I referred to the data mesh architecture, and that's really the diagram on the left-hand side here. And at the bottom, you've got your applications, and the middle blue boxes represent the platforms. So the platforms are aggregating the information from their applications into a common product, and then that common product is being shared back into our knowledge map. And so as we've moved from the application level, where everything is application-centric, that we then go to a data product-centric piece. But even in the data product, you'll see the purple box is clinical study, the concept of clinical study, and it appears across multiple platforms because data from those platforms are generated and then it needs to be combined back together again, and that's what is happening in the knowledge graph. So we've transformed ourselves from that application-centric to now representing the data in a data-centric, or maybe more correctly, in a science-centric fashion, and we're using the terms and the preferred labels of the scientists now in that data, so they can ask their questions and explore that information space. So this is bringing it all back together. Start with meaning. Start with identifying your things. Describe the things. Work with your subject matter experts to identify all the terms. Have a consistent URI strategy, and then make it easy for the scientists to incorporate that back into the data. Sorry, I said scientists. I should have said scientists, IT colleagues, anyone who's generating data or is curating data. And then that's going to make it a huge improvement in our reuse of the data. It's going to allow interoperability for whatever we want to do. But also, sneakily, we've now got it all aligned, and we've managed to get everyone else to do all of that hard work of cleaning up and harmonizing that data for us, and we can just plug it into the graph. So the take-home message is, we want to deliver information discovery capabilities. We want to go beyond a reverse index search. And that is what is required to allow us to evolve the science and the greater granularity that's associated with it. It creates new demands on our data, and if we're going to build these complex data structures, we're going to need librarians to help us do this. And maybe, I'm looking forward to the talks later on about LMMs. I'm hopeful that they're going to provide us another way to help navigate this space. Use common patterns, so standardize. Don't be overly proud of your cleverness. Just standardize it, right? Because it's the data at the end of the day that matters. So it's great, open source. It'll get you moving quick, but it's better to spend your engineering expertise on working on the data than it is on the infrastructure. Work out how to blend the relational skill sets that you've got with the semantic skill sets. Be pragmatic. Do what you can with whatever skills you've got wherever you need to. And design for extensibility. So assume that things are going to change, that you haven't got it right, and that the new ideas are going to come forward. And then this is all based on driving that interoperability. So we invest in controlled vocabularies. We build these SCOS vocabularies that describe unique things. And we do it in a coordinated and organized fashion, so an editorial governance is required. and hide the semantics, because 80% of the organisation just don't care. But 80% of the organisation will do an awful lot of work for you, which will let you do the work. So I've managed to pass 60% of the wrangling onto the rest of my IT colleagues and scientists, and I can focus on the semantics and doing the thing that interests me. So this presentation is a summary, an aggregation of an awful lot of work by an awful lot of other people, and I'm just the face presenting it in many cases here. So I just want to take a moment to recognise not just our internal people in my team, the Data Find and Integrate team, but all of our collaborators across AstraZeneca, but also the Pistoia Alliance and the FAIR implementation work stream within that we've worked with, and hats off to all my colleagues in that in other pharmaceutical companies who have been so generous in sharing their ideas. And I think that was the last slide. So hopefully there's time for a few questions.
So, yeah, thank you, Ben, for this great keynote. Do you have questions? If you have questions, please go to a mic in the room in order to be able to, our stream users to hear you.
Yeah, thanks a lot. Great presentation indeed. So, imagine you are in a larger organization where people who already embrace these concepts like data product, data mesh, and all what you described. But they don't come from the knowledge graph community, the semantic web community. You tell them use SCOS, use JSON-LD, and they say, we have our own way to do this. And imagine also this is a large community, much smaller than the one embracing knowledge graph stack. How do you bring them on board?
We're bringing, so I come from a large organisation, we're 70,000 people. We've got a pharmaceutical companies, effectively 3 businesses. There's an R&D business, there's a manufacturing business, and there's a sales business. I sit in R&D, so I can influence R&D. We really asked, what is it they're trying to do? What is their pain? And we all know the pain, and I've got this data set, I don't know where it's come from, I don't know what it is, there should have been a data dictionary with this, there wasn't a data dictionary. Is this column really the same as the column in this one? That's the pain that people have. So how do we tackle that? And that's what we focus on. And we don't talk about building SCOS vocabularies, we talk about building vocabularies to enable them to relieve that pain. So we hide all of these things about JSON. It might be really clever if we said, oh yeah, we'll produce all of our data in JSON-LD format, but it doesn't really matter. If they want to produce it as a CSV file, where one of the columns contains the PID, then we're probably pretty good anyway, right? So the answer is not to hammer on about the things that we care about, talk about the things that they care about, and say, just do it in the way you want to. Because if they all have PIDs in all of the data, I've got lovely tools like eccenca's corporate memory, which will let me take that data and just transform it to RDF from whatever source it needs to be. So let's not say you've got to work like this. Work like you want to do, but include this value in there. Yeah. There is a slightly more nuanced aspect around the interoperability piece. And this comes from Martin Romecker at Roche, who makes the really valid point that there are actually, we refer to it as relaxed and strict FAIR, or interoperability. So relaxed interoperability says, ensure the terms that you use to describe that concept are included as alternative labels in the vocabulary. And that allows us to deal with scenarios where we might be dealing with a SaaS service where we can't add another column in to hold the PID. They can achieve relaxed FAIR by making sure that the terms that they're using to describe the thing are included in the vocabulary, so you then have the interoperability. It's a 2-step process because you have to look it up to get what the PID is, but at least it's there and you have confidence in it. That does require you to produce a data dictionary, which you should be producing anyway, that makes that statement. And the other one is the strict FAIR, where you include the PIDs in your data, in which case you're all good to go and you have machine readability as well. So focus on their pain, and they don't care about the graph and they don't need to know about the graph. They just want to know that, can I join my data together? And that's enough to push it through in our experience so far.
Yeah, great. Thanks a lot. Yeah.
You have a question, Hans-Christian?
Well, yeah, I actually wrote down 2 questions, so sorry, my voice is a little bit funny, but I think it's interesting to also contextualize for the people that are not in the life science or biotech industry, why you got so much leeway from your board and so much money, to build this beautiful thing, because obviously it's a multi-year effort, and there could be concerns of the cost, and do you see the end of the tunnel at some stage, and why, does your board support this? Why is this so important for your entire industry? Why is the Pistoria Alliance into this? For everybody in this industry, why is that so relevant? I think that something that didn't really come across so well.
Yeah, I didn't. You're right, Chris. I didn't feel that aspect in. I think I'm very lucky. Okay, I've been doing this for a good 20 years in this space, and landing at AstraZeneca really landed me in a position where the coalition of forces all came together at the same time. There was a whole load of interest in doing data science and investing in data scientists, and we got that investment in the need to organise our data. I don't think I'm giving anything away when I say that we hire a lot of colleagues from the EBI in Cambridge, so the European Bioinformatics Institute, which is a big proponent of building linked data and has been one of the big enablers in the life sciences space. So we get these colleagues coming in, and they come in and they say, oh, I'm going to be in a company and all the data is going to be really well organised and I can do really exciting things. And they come in and they say, this is even worse than the academic data. And it's true, because the whole industry, the whole things are driven around submissions for your drug to get to market, and that's what it's driven for. And they don't design anything for reuse. And we're trying to re-engineer reuse into this. So the desire to have the data science and the recognition that we had to do something about our data was the driver. And we, back in 2018, we had a goal that said, at the board level, 80% of the data in AstraZeneca will be FAIR by 2025. That has quietly been dropped and hidden, but it created the momentum to do this. And the therapeutic areas, so the business side, the actual science teams and organisation, decided that if they were going to do this, they would invest in creating a group within their own thing, so not in IT, called the Data Office, that would be responsible for dealing with things like compliance issues. So, when we want to reuse our clinical data, we've got to ensure we're compliant with the informed consent of the patients that participated. So there's aspects of it. Trust frameworks. So understanding, what are the critical pieces of data that we're generating, that they're able to be reported to help drive the standards for clinical data, et cetera, et cetera. And also building data services to try and help clean up the data, and that's where we landed. And I'm very lucky that Matthew Wooddock, who's my boss, effectively acts as a patron. And he's the expert that goes out there, and he has that talent for surfing the budgetary wave and protects us. And as long as we're still doing what he believes in, he gives us that largesse to actually get it done. So I'm very lucky of where I've landed, and it's probably a very unique situation in AstraZeneca.
Okay, thank you, Ben. And maybe I can add 2 few cents on this, because I think what makes me proud, in working with you guys, is at the end of the day, I think we're, as a society, we're at a point where creating new drugs is so expensive now, right, that we're looking at billions of dollars for a new product. And that again narrows down the scope of focus of these pharma companies, because you can only research products for large niches, basically, right? So I don't know, we know 40,000 diseases, I think, and we have products for 2,000 or something like that. And so 38,000 diseases are not being researched, basically, because the business case isn't there, because the cost is so high. So what excites me about this case is that if we can reduce, or increase the productivity of your scientists, and you say from, give them another 40%, because they don't spend 80% of their time, but only 40% of their time data researching, will make them more productive. And if you look at the greater scheme and you can say, okay, instead of 2 billion, take 40% out, the product comes to market faster, more reliable, higher quality, patient safety, and all those things. So from a meta area, this is really relevant for all of our lives and the loved ones that you have, because we need to find a way to make life science and bioscience more productive in the future. And this is really the best role model globally. That's why this presentation is so relevant. AstraZeneca is the thought leader in this industry, and the work that Ben has done is a lighthouse, and we're together in the Pistoia Alliance. I don't know, it's more than 30 pharma companies in there. They're all following his footsteps. He's a role model here. So, say thank you to him when you leave the room, because the work they're doing is saving lives in the future. So thank you, Ben.
I will say, I'm just... Thank you very much, Chris, but I must give credit to the team in the FAIR implementation team, and Martin Romecker is my role model, and I'm doing a lot of following the great work that he did there. So we share ideas in that collaborative fashion to help us all move forward, and that's the point of Pistoia. And I will say that, Chris, your point of could be said, Ben, but you're creating FAIR for AstraZeneca. How is this fair with Roche or with rare diseases or NGOs and those sorts of things? You're absolutely right. What we now need to do, and what we're now working on in Pistoia, is trying to agree that common interoperability. So what public vocabularies can we all sign up and say, we will include these identifiers in our data, so that we can have interoperability between these islands of FAIR that we've created within our companies, between CROs, between universities, between NGOs.
Well, Ben, you're dishing this up for me. Thank you for teeing this up for me, because I think another one that we get when we talk to our clients and we talk about knowledge graphs in this technology, obviously there is a lot of debate about open source software. And I think what I heard you say in the presentation, I think that's really cool, is that you're suggesting not to get entangled in tool development and focus on scaling value, right? So collaborating with others who already have ontologies, work on that, bringing them in, creating value in your organization, focus on your customers in the organization, and creating value for those customers. Don't get entangled into building software, because software is there already. And maybe if you can say a few words, obviously, I'm saying this all the time. Customers just don't want to listen, but maybe they'll listen to you. So I like to hear that anyway. So.
Yeah, so thank you, Chris. The data is everything. Let's remember the data is everything. Let's put as much resources into the data and getting the data fair. That's where the value is. It's not in being clever enough to be able to combine open source tool with A and B and get them to work together. Let's just get away from that. Let's just move to this place. And we're seeing the market now with companies like eccenca being able to allow us to focus on the data, and that's where the value is.